Good afternoon. My name is Jose Abrams from the Department of Biomedical Engineering, and today we're going to be talking about the subsystem 1 in electrical sensor weight gain, which is the electrical and control system. Today we're going to be talking about 5 main points, starting with the interface diagram, followed by the detailed analysis design studies. Next, we have the design specification drawings, MOP compliances, and finally, to finish off, the complete project planning for future phases. Starting with the interface diagram, we have a block diagram that represents a simple negative feedback control system. To find the open loop transfer function, we have to set k to 1 and then use a straight-in line approximation to draw a Bode diagram and investigate the stability of the closed-loop system. We only need to calculate a few points to sketch the Bode diagram. On A, we have to determine the maximum gain that gives a gain margin of 8 dBs and a phase margin of 60 degrees. Next, we have the suppose that for the position accuracy, the gain must be set to 100 and then investigate by using the Bode diagram drawn above the stability of the closed-loop system. If unstable, design a lead-lag network so that the system has a gain margin of 6 dBs and a phase margin of 60 degrees. On figure 1, we can see a block diagram of the negative control system and a hint on figure 1.2 for the lead-lag network. Here we have a flowchart for program logic, which we start off with the block diagram with a negative feedback, as we saw on figure 1. We set k to 1, we find an open loop transfer function, we calculate the amplitude in radios, and multiplication becomes summation. We straighten the line, draw the body diagram, and to find stability, the maximum gain needs to be set to 7 dBs and the phase to 60 for the position accuracy. And if the program is stable, it ends. If not, we have to find a lag time constant and the lead network with the phase of 60 and a gain of 6. We do the body diagram and find corner frequency, and the program shall end. Here we have our transfer function, and on the right our closed system, our negative feedback closed system. As we saw on the flowchart, multiplication becomes summation. So we can find our transfer function, which here on the right. Once we calculate our transfer function, we open up MATLAB, set the codification for to access a Bode diagram, which is a very helpful tool in MATLAB. As we can see here, we have on the top we have the magnitudes in dB, and on the bottom the phase in degrees. And in the x-axis we have our frequency on rads per second. As we can see here, the dBs is set to negative 15.1 and our phase is 0.454 degrees. Here on figure 2.1, we can see a Bode diagram with no gain. As you can see, the frequency is at 38.2 and the magnitude on A, that's on the magnitude, and on the phase, we have a frequency of 60.3 and a phase of negative 206. And to finish off, for the detailed analysis, we have the plot for the with a gain of 100. As you can see, the magnitude on the top right, on the top, and on the bottom, the degrees with its proper shape in its frequency on rads per second. We have a flowchart for the microcontroller. It starts off with its initiation standard mode. Then we have the ultrasonic transmit and receive sound waves. In case that no sound wave is received, it should continue on a loop. If any obstacle is detected, the ultrasonic will calculate the distance. In case the transmission is sent, it's gonna emit a signal to the vibrating motor, to the LED light, and to the vibrating and to the buzzer to let the patient know that some obstacle is interfering its way. Now we're gonna be talking about the design to specification and drawings. As you can see on figure 3, we have a circuit schematic indicating all its proper connections of all the electrical components connected to the Arduino. As we can see on the bottom left, we have the item and its quantity. We have the Arduino, it's only one, the ultrasonic sensor, the buzzer, the vibrating motor, a resistor, the LED light, and the battery. As you can see on this schematic, everything is connected to the Arduino, which is basically doing all the work, and the battery it's emitting its power. We have the ultrasonic sensor, we have the buzzer, we have the vibrating motor. And here on the next slide, we can maybe see have a better understanding of how it's gonna be working. We have here we have the first component is gonna be the ultrasonic sensor, which is connected to the breadboard, you can see, and it's directly connected to the Arduino. On the buzzer, which is the left circle on the top, it's the buzzer is connected directly to the Arduino. The vibrating motor, it's the smaller circle to the right of the buzzer, which is also connected to the directly to the Arduino. The number four, it's the Arduino itself, which is the one's gonna be controlling everything. Our fifth item is gonna be the LED light, which is the red one we see between the buzzer and the vibrating motor. And finally, we have our battery, which is connected directly to the Arduino. And on the bottom left, we can see the on and off switch for controlling the system. As we can see here on figure 4.1, which is the same as the slide before, the difference is that we have the range we set to the ultrasonic sensor turned on. As you can see, this figure is an obstacle at more than 40 centimeters, which is not too dangerous for the patient, so it's not gonna be sending a signal. But on this slide, we have the obstacle entering the 40 centimeter range, which activates the buzzer, which we can see with emitting its sound on the top left corner. We can see the LED light between the buzzer and the vibrating motor with an exclamation point indicating that it's on. And here on our next slide, we have a video of this circuit running. Let me play it right now. As you can see, this is the switch to turn and off and on the system. We turn on the ultrasonic sensor. Nothing is happening. It's off. Now it's on. Nothing is happening because it's more than 40 centimeters. Now it reaches our range and it turns on, emits the buzzer sound. Our LED light is on and the vibrating motor should also be vibrating, alerting our patient that something it's on its way. Oh, sorry. Here we have our ANSI drawings for all the components on the electrical system. We have the battery with its all its dimensions, same for the ultrasonic sensor. Let me see, we have here a vibrating mini motor disc with its dimensions, also the Arduino. On the next one, we have the LED light and the speaker. Now for the MOP compliance verification, we're gonna be starting with our first MOP, which is enhance the system availability by reducing sharp edges and improper bends, resulting in a safe wire route. Yes, we did comply with this, and we verified it on phase CE1, which my partner Gustavo was working with the housing and all the housing where the electrical components gonna be, and we set it up for a very safe route and no sharp edges or improper bends that will result in an improper wire routing. For the second MOP, we have that the sensor will be powered by a 5 volt and must be able to detect obstacle at a range of 5 to 8 feet. Yes, we did comply. We verified it on this phase. As you saw in the video, we have our different range detection with where the ultrasonic is gonna be sending the signal if it's more than 40 centimeters, and if not, we can adjust that. It's basically on the program, on the codification on MATLAB once we construct our physical project. Then with the third MOP, we have to utilize a chargeable battery with a minimum of 200 to 400 charging cycles with an accessible charging port included. Yes, we did comply and we verified that on phase B. For the fourth MOP, we have the proper attached sensor in the correct angular position with no nearby interference. We also comply with that and we verified it on phase C1, 2. The same as the first MOP, my partner Gustavo was working on the handle on the housing case, and we set up once I sent him the how our electrical circuits was gonna be, he decided where we're gonna put the ultrasonic sensor, which it's like kind of vertical on the housing, and it has its proper fitting with no nearby interference. And for the last MOP, we shall ensure that all current flow is in its proper direction. And yes, we did comply and we verified it on C1s. As you guys saw on the video, we have its proper flow current. Now moving to the verification budget, we have the first item, which is an electronic component kit, which contains the Arduino and all the stuff with the breadboard, everything included. We only needed 4 vibrating motor sensors, which were 549. I'm sorry, the electrical component kit was 1599. We used the Tinkercad software, which is an open source, which was free. And for the MATLAB and for the diagrams or the ANSI diagrams, we used the student version of MATLAB, which was completely free. And finally, we need to add a battery, a 9-volt battery, which has a cost of around 3.25 cents for a total of $59.73. And as we stated, I think it was phase A, we are below our estimated budget for the electrical and control system. Here we have the complete for a project planning for phase 2. As you can see, we're going to be working on then on the first, second, third, and fourth week of September. And the deadline for our C2 presentation, it's going to be on October 1, 2021. For any questions or more information, you can contact me via email or Blackboard. Thank you for your attention.